All right. Section 3.4, velocity, acceleration, and other rates of change. We want to start today with an interesting geometry problem. Let's say we want to find the rate of change Okay, so when I ask for the rate of change, from this chapter, I'm really asking you to find what? The derivative. Okay, so when it says find the rate of change, really what I'm saying is derivative, okay? We might even put derivative there. You'll never see it written like that. And the problem, you'll just be asked to find the rate of change, and you'll be it's just understood that I mean find the derivative of the area, capital A, of a circle with respect to its radius. So we'll find the rate of change or derivative of the area, capital A, of a circle with respect to its radius. So we need a formula that relates the area to the circle's radius. And what is that formula? No, not quite.
Pi r squared.
Pi r squared. For area, it's pi r squared, but hold on to that. So the area is pi times the radius squared. And what we're going to do is we're going to take the derivative of this, and it told us to do it with respect to the radius. So we're going to do it with respect to r. So we're basically finding the derivative of area with respect to radius. So I treat radius like my variable, like my x, and I'm just going to do the power rule on this. Pi is just a constant multiple. So I'm just going to end up multiplying it in times the derivative of r squared, basically. And if I derive r squared, I'm going to bring that 2 down. I'm going to decrease the power by 1. And I get the derivative of the area with respect to the radius, which happens to be what? That's the circumference of the circle. Huh. Coincidence? Interesting. Okay, let's say that we also wanted to evaluate the rate of change of A at r equals 5 and r equals 10. Well, if we wanted to evaluate the rate of change, it just needs to evaluate the derivative at these values. So we already have the derivative 2 pi r. We're just going to plug in 5 on one of them. We're going to plug in 5. So at r equals 5, the derivative with respect to r would be 2 pi times 5. I'm just plugging into 2 pi r right there, which would be 10 pi. And at r equals 10, the derivative with respect to r be 20 pi. Now, let's see if we can come up with some units for this though, and what these values mean. Because that will help us to understand what this is talking about. We're talking about a rate of change, so we're talking about something that's changing. So, and it's easy, the easiest way to come up with what the units are gonna be is to look at your derivative notation here, especially when it's in this notation. We're talking about units of area over units in radius. So the units here would be inches squared per inch of radius. Your area unit is inches squared, your radius unit is inches. So what this is saying is that when the radius is 5, the circle's area is changing at a rate of 10 pi square inches per 1 inch of the radius at that instant. Later on at r equals 10, now it's changing at 20 pi square inches of area per inch of radius. So it's changing, changing at different rates there from one value to the next. That makes sense though, because the original function, if we think about the area formula as a function, that might be kind of weird to think about it like that, but it can be a function. That's just like an x squared. It's just like pi times x squared. So if it's r, so that's like a quadratic function. So we know that just the way that that's, think about that. It's going to, if you think about that curve, the tangent slopes are going to change. These are all, you can think about rate of change of tangent slope too. Those tangent slopes are going to change from one value to the next. Okay, that's what the tangent slopes would be at those instants. Questions? All right, so we're going to look at some interesting applications there. Not just in this section, we're not just going to look at the physics. I know the title, from the title, yes, we're going to talk about velocity and acceleration. Absolutely. But you're also going to see some other applications in this section, even some business applications, just to mix it up, because we can talk about cost and revenue and those kinds of things as well with calculus. But by all means, yes, of course, we're going to talk about some of the physics applications. Isaac Newton being one of the fathers of calculus. Hello, yeah, that's why. All right, so position, velocity. Let's talk about the relationship between these three quantities: position, velocity, and acceleration. We often denote the position function, which tells where an object's at. We often denote it as s equals some sort of function of t, where t is time. But we often denote the position as s. Why s, I don't know, honestly. We could call it whatever though. You can call it anything. Sometimes it's even called x. I've seen that before too. It just depends on whatever you want to call it. I mean, it's just a variable. But we do usually write them in terms of t, the function in terms of t, meaning that it's a function of time. They do usually use t for that. Velocity is v of t, and it is the first derivative of position with respect to time.
At this time, seniors A through D, please go to the library. That's seniors A through D, please go to the library. That's last name A through D.
Have fun, go pick out a good book. It's the book fair today. Okay, velocity is the first derivative of position. Just a note here, speed though is a little different. How is speed different than velocity?
Velocity is a vector quantity, whereas speed is a scalar.
That is true. That's a true physics definition right there. But what do you mean by vector quantity and scalar quantity if I'm just a regular old average Joe and I don't understand that stuff?
Velocity has direction, whereas speed does not.
Absolutely. Because it's a vector, then it's got an actual direction as well. Okay, so velocity can be positive or negative depending on the direction that you're moving. Okay, and it's all about your point of reference, where you're starting at. Am I moving towards that or away from that? Okay, so velocity can be positive or negative. It's got direction to it, whereas speed does not. Okay, speed is actually the absolute value of velocity. Okay, if you take the velocity function, the absolute value of that's speed. Okay, just to note, you got to be careful in a problem. Are they asking me to find the velocity or are they asking me to find the speed? There's a difference. Okay. Those of you that had AP Physics last semester or AP Physics last year or physics, just regular physics for that matter last year, or maybe you will have physics, you're going to see all this again. Except when you see it again, for you, I'm just telling you, you can use calculus to solve some of the problems, and everyone else in the class will have to do it the algebraic way. So there's an advantage here, I guess, in a way. Yeah. I don't know exactly all the connections. I do know the connections, but I don't know exactly all of the advantages you would have, or, and everything. But yes, it definitely, from past experience with students that have taken both, I can vouch by what they said that it would help. All right, acceleration. The acceleration function is usually denoted A of t. Acceleration is the first derivative of velocity with respect to time. So if I take the derivative of velocity, I get acceleration. If you think about it, that's what acceleration is. It's a change in velocity. Okay, we're changing velocity. So I'm accelerating if I'm moving and then I start to go faster. Okay, there's some acceleration there. Okay, that's the idea behind that. It's also, because velocity is the first derivative of position, then acceleration will be the second derivative of position. Now, your book actually has this next term in the next section, but I go ahead and just introduce it here. We won't do a whole lot with it here, but you might see it. And that is the derivative of acceleration, which is a jerk. This is the first derivative of acceleration with respect to time, which also means it's the second derivative of velocity with respect to time, which means it's the third derivative of position with respect to time. Basically, position, derivative of position's velocity. You derive it again, you get acceleration. You derive it again, you get the jerk. We're talking now about a change in acceleration. This is the feeling you get when you're on a bus that's making like sudden stops. Okay, it's the actual movement that's causing the, if you're on a bus and you've got a cup of something or whatever, and they make this sudden stop, and you end up spilling some of it, your drink out of your cup or whatever. That's that change in acceleration that is causing that. Okay? Lovingly, if you want to tell someone to stop being a jerk, tell them to stop being a third derivative. Don't be a third derivative. I saw a t-shirt one time that said, don't be, just had that. Don't be a jerk. All right. Let's also recall, you may remember if you've had physics, an equation called the free fall. S equals 1/2 gt squared, where g is what? Gravity. It's the acceleration due to gravity. It's the acceleration due to gravity. We have some constants for g, because gravity here on Earth is, there's a set amount there. So we have some constants for g that we use for free fall. In the English or customary units, g is equal to 32 feet per second squared. So it follows that your free fall equation then would be S equals 1/2 times 32 t squared, or 16 t squared. That's if we measure in feet per second squared. In English, our units that we use here in the U.S., because we have to be different. Metric system uses slightly different values here, slightly different constant. Gravity in that system of measurement is equal to 9.8 meters per second squared. So when you plug that into your free fall equation, S is going to equal 1/2 times 9.8 t squared, or 4.9 t squared. So if you drop an object, it's going to fall, depending on your units here, whether you're using meters or feet for your measurement of position, it's going to fall according to these two functions. Okay? When I take a marker and I drop it, it's falling because due to gravity it's going to fall down. and it's falling according to whichever unit I want to use here, whether I'm using feet or meters for my position here, according to these functions. Alright, so let's look at an example of using this information. So for example, a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of S equals 160t minus 16t squared feet after t seconds. The first question, how high does the rock go? Does it matter that the rock's heavy? I mean, what the rock's made of, maybe because, of course, we talk about all of this, but there are other forces that are acting on things when they're dropping from free fall, namely friction from the air, because we're not in a vacuum. Maybe what the rock's made of, but not as far as it being heavy, no. That's really just kind of in there as a distractor. Okay, would it matter if it was a heavy rock or a light rock? Not really. But it's going straight up with the launch velocity of 160 feet per second. That may have affected, because based on what it's made of, it may have affected how much that dynamite blast was actually able to do to the rock. Sure. Anyways, it reaches a height, though, of S equals 160t minus 16t squared. So there's my position function right there. after t seconds. How high does the rock go, not reach? Well, I was thinking, maybe I was gonna write how high does the rock reach or something like that. Anyways, how high does the rock go? That's what I've got written here. So if we wanna know how high does it go, what do we know about that? So it starts here on the ground, blast, it goes up, and then it's gonna obviously come right back down at some point. So if we're looking at that point there, the highest point that it reaches, what do we know about the rock right there at that instant? The velocity would be 0. Okay, the velocity would be 0. That means your what would be 0 when we think about it in terms of functions? What? Velocity is the derivative of position. So we're going to take the derivative of that function right there and we're going to do what with it? Set it equal to 0. Okay, that's how we're going to figure out where it's at its highest point. Okay, the derivative of that position, that's position right there in the problem. So if we take the derivative of that and then set it equal to 0, we're going to find where the velocity is 0. We're going to find that maximum point, that high point. Okay? That's where the tangent line would be horizontal. Dare I say, to make the connection to something else we've already done. So, we take the derivative of this with respect to t. Let's do it term by term. 160t, what's the derivative of that? 160. And then I derive negative 16t squared. It's going to be minus 32t. And I'm going to set that equal to 0. So 160 minus 32t is equal to 0, and I want to solve this. So I can subtract 160 or add 32t to both sides, whatever you want to do. Move it however you want to. Divide by negative 32. And negative 160 divided by negative 32 is what? 5? T equals 5. So that tells us that the velocity was 0 at t equals 5 if we really answered that question, though. But what can we do with that? Plug it back into our position function, because that'll tell us where it's at that instant. So we know it occurred at time equals 5 seconds. Now we just got to figure out where were we at time equals 5 seconds. So we're going to plug that back into the position function to answer this question. So this means that velocity is 0 at time equals 5. So what is the position? We're going to find S of 5. That's going to be 160 times 5 minus 16 times 5 squared. We can plug all that in the calculator and we get 400 feet. Double check me, but that tells us that it was at 400 feet when the velocity was 0. Okay.
Teachers, please excuse the interruption. Seniors with the last names E through G may go to the library at this time. Seniors with the last names E through G go to the library at this time. Thank you.
Y'all checked out what the books look like? Do you have an idea of what you want? There's all sorts of books down there. I'll have to ask some of my academic team kids if they got Percy Jackson, because they love the Greek mythology questions. Morning the flies. All right. So that would give us the object where it was at time equals 5. For those that just missed out on this first part of this problem, we're blasting a rock up and straight up in the air with the dynamite blast here. We got our position function right here, and we want to know how high the rock went. So we took the derivative, and we set the derivative equal to 0 because obviously if it's going straight up, it's going to reach a point where the velocity is 0 because it's slowing down as it's going up, right? Because gravity's acting on it. Okay, so it's going to slow down, and for just an instant, it's going to come to a stop before it turns around and comes right back down. So we found where the velocity was 0, and then we plugged that value for time into the position function to figure out what our position is at that time, to see how high the rock went. We're going to ask ourselves a little bit different question now. What is the velocity and speed of the rock when it is 256 feet above the ground going up and coming down. Why did I say going up and coming down? Starts on the ground, blasts. The rock goes up in the air. Okay, we already know that it's going to reach a height of 400 feet. So at 256 feet up off the ground, there's going to be an instant where it's there, then it's going to go up to 400 feet off the ground, and then it's going to start coming back down, and there's going to be another instant where it's at 256 feet. It's just one instant it's going up, and the other instant it's coming back down. We're going to see how the velocity is different here. Okay, you may already know kind of the way it's going to be different there, but we're going to see that for sure here. We need to figure out when does that occur, basically. When is it going to be at 256 feet? The first time and the second time. So where can I put 256 feet in this problem? What is 256 feet? What? That's a position. So we're going to plug that in for S. In the original problem, we can plug that in for S. So S is going to equal 256. So 256 equals 160t minus 16t squared. We need to solve that equation. Well, that's a quadratic equation. How are we going to solve that? Well, We can move everything to one side to start with. Move everything to one side, have it all equal to 0. So that's going to be 16t squared minus 160t plus 256. I bet you every one of those numbers, I bet 256 is divisible by 16. So we could just divide through by 16 really quickly to make this a whole lot easier. As long as we do it to everything, term by term, it's fine. We can do that. So that's going to give us t squared minus 10t oh yeah, 256 happens to be 16 times 16. It's a perfect square. So that's going to be plus 16 equals 0. And we need to solve that equation. Now that looks a whole lot more manageable. We could factor that, baby. I bet it factors. I want 2 factors of 16. Now A's 1 too on top of that. That makes it even easier. A's 1, and my AC, A times C is 16. I want 2 factors of 16 that add up to 10 or negative 10, so I'm going to make them both negative. I want 2 things multiply to 16 but add up to 10. 8 and 2, right? So that will factor, and because it's a negative 10, I got to make it negative 2 and negative 8. This will factor as t minus 2 times t minus 8 equals 0. And because the zero product property from algebra, I can set each of those equal to 0, t minus 2, t minus 8. And that's going to come out to be time equals 2 and time equals 8. So it's going to reach 256 feet after 2 seconds, going up. It's going to go all the way up at 5 seconds. It's going to be at 400 feet. And then it's going to come back down, and at time equals 8 seconds, it's going to be at 256 feet again. Okay, we still haven't answered the question though. We found out when it happens, but now we want to find out the velocity and the speed. But if we find the velocity, we already know that speed is just the absolute value of velocity. So we'll figure out what speed is if we just find velocity first. So let's find the velocity at 2 and at 8. Velocity at 2, we already have a velocity function too, right there. We found it over here. So we don't have to redo it. We can, these build on themselves, okay? And that's the way your homework problems are going to be today. You'll have less problems because they build on themselves and they have like 4 parts to them. Okay? The velocity is 2. So plug in 2. That gives you 96, I think. And what would the units on that be for this velocity? Because we don't like naked numbers. Feet per second. I'm going to abbreviate second with S now. I don't know why I was using SEC anyways for that. Whatever. And then at 8, 160 minus 32 times 8, you get a negative 96 feet per second. Why is it positive going up and negative coming down? What?
Direction.
Just kind of where you're, because, you know, our point of reference here is where it started at, from the ground. So it's heading away from the ground going up because it's going
Teachers,
up.
please excuse the interruption. At this time, we need seniors, last name H through L, to please go to the library at this time. That's seniors with the last name H through L. Go to the library at this time. Thank you.
Was it crazy down there?
There's only like 20 people in there.
They're calling them down in small groups, I mean, obviously, cause they don't wanna end up having a super spreader.
The seniors are gonna be really thin, 'cause we're such a small class anyway, and we have people out for
Co-op.
co-op and.
Yeah, they'll have to have, yeah. They're gonna be doing this every month.
Every month, I thought they were just doing it like once a 9 weeks.
No, it's supposedly.
Yeah.
Around this running stuff. Cause everything she just did, she's gonna have to do every month for the next 5 years. To get that
At
set up.
least.
5 years?
At least, unless
they
they
don't
get
get the
more
grant
funding
again.
for it.
Wow. You have your own library.
She said seniors will get 5 books.
Dude, that's like $15 a month.
We came up,
You just sold it.
you go a whole year getting 12 books and plus it sounds like every time you get $300. We was checking it out.
Well, let's get the,
Plus, if you went, you can tell her what book you want for the next month, and she'll order it for
Yeah.
you.
Yeah, you can get a specific book if you request it. Alright. So, the speed at both instances would be what?
96.
Just 96, because if you take the absolute value of the positive or the absolute value of the negative 96, both instances you're getting 96 feet per second. Okay, but does it make sense? It's positive going up because your point of reference is the ground. It's heading away from the ground. And it's negative coming back down because it's heading back towards the ground. I could also ask you to find things like, and maybe we won't write this out necessarily, the acceleration. Okay, just take the second derivative. If you do that, if you take the derivative of this, you should see that it comes to be negative 32 in that instance. 32, that constant that we said that we would get anyways, that's why you're getting that. Okay? And that units on that acceleration would be what? Feet per second squared. Okay, feet per second squared. All right, I could also ask, when does the rock hit the ground? When would it hit the ground? That would be at 10 seconds. Why 10? The easiest way to think about that is what? How did you get 10?
Well, we got 5 here when it reached the peak, so it goes 5 then.
Yeah, because of symmetry. If it took 5 seconds to get to its highest point, it's going to take another 5 seconds to fall back down to where it started. So it's going to take a total of 10 seconds. Just because of symmetry like that. The way that works. Okay. But you could also verify that algebraically if you set the position function equal to 0, because that's, if you're 0 feet off the ground, you're on the ground. One answer you're going to find there is t equals 0. Well, duh. The rock is on the ground before the blast happens. Okay? And then the other instance that it's going to happen would be t equals 10. 10 seconds. Okay? Questions? Okay, so we're going to practice a little bit with this stuff. We'll do a little more maybe with section 3.4 tomorrow with some business applications. But here's what I want you to look at on page 135. Starting on that page. 1, 3. I know we didn't do an example with a graph, but I really want you to try number 9. I know we probably will end up having to talk about that one. That's okay. And then I'm gonna have you do number 13. 13, your free falls are a little bit different because you're on the moon. So your gravity, acceleration due to gravity will be a little bit different. It tells you that in the problem though. So your equation will be a little different, okay, because you're on the moon. That changes once you're on a different planet. Okay, this is all on Earth. I didn't mention that, but this is on Earth. These are worth knowing because you see these more often than anything else, but you know, every once in a while you get a curveball. Oh, we're on a different planet now, so that changes everything. Try 15 as well, which I think kind of continues number 13. 13 you're on the moon, now 15 instead you're back on Earth. As you calculate something similar. We'll stop there. 13 itself has 5 parts to it, so. These can easily be an FRQ. I didn't realize you were taking